clearly? Okay, thank you so much. I want to welcome everyone to my lecture today. Today, I'm actually going to walk you through another exciting topic in statistics. And of course, today, we're actually going to start a new topic called Axioms of Probability and Expectation. Okay, so give me 1 second. I'm going to share my screen. Okay, so like I said, today, the focus is basically going to be on axioms for probability and expectation. What do we actually mean by axioms? Okay, axioms, by axioms, we basically means rules. Okay, we basically means rules. You know, in this lecture today, I'm actually going to unfold some rules that guide probability and expectations because in a stochastic world, in a probabilistic space that we live in, we basically, going to work with probability and expectations. And you know what? We basically need some rules, okay, that guides probability and expectation. So that's going to be the focus today. Now, in the outline, like I said, I'm going to walk everyone through probability axioms. And we're also going to talk about linearity of expectation. Okay, yesterday, we actually talked about linearity of random variable where, random variables are added together. If they originally follow a different probability distribution, then we can seek the probability distribution of the sum of random variable but today, the focus is basically going to be on linearity of expectation, situation where we are adding expectations together. And I'm also going to walk you through some illustrative examples as well. Okay, and in addition to that, with the illustrative examples, we're actually going to visit some selected discrete probability distributions like discrete uniform, like Bernoulli distribution, and like binomial distribution. So we're basically going to visit 3 of them today. We're actually going to look at some property like the expectation, the variance, and so on like that. And that is basically going to be the illustrative example that I talk about. So right now, we're basically going to start with axioms. Okay, like I said, when I say axioms, I basically means rules. Okay, we live in a world, we got a lot of rules. Okay, just like before you can actually live in state of Minnesota. Of course, the Minnesota have laws, regulations. Okay, we also have rules that guide the probability and the expectation that we're going to talk about now. Okay, now the other time, uh, I actually said if we have a random variable x, okay, a random variable x, a variable is anything that is liable to change, okay? Now I want it to be cinder x now, okay? Cinder x now probably as gas price, okay? We look at that, the gas price is a random variable, it continues to change, okay? And you know what? The expectation of x is basically going to be, our guess. Okay, that's gonna be a guess. Okay, that's gonna be our guess before the gas price is observed. Before, before I visit stations, gas stations, to be able to know what the price is before that is observed. Okay, the what I have in mind, like what the guess is actually expected value of X, so which we call the mean of X. Okay, now we have a raw now. Okay, for instance, we basically want to talk about the expected value of X and Y. If you take a look at X, if you take a look at Y, X is a random variable, Y is another random variable. X has its own sample space, and Y also has its own sample space and mean. X has its own support and Y has its own support, and if I had X and Y all together, okay, the expectation of the addition of these two variables is basically equal to the sum of the respective expectation. This is one of the axioms of expectation, that when I have the expectation of the sum of a random variable, the expectation of the sum of a random variable is basically, the addition of the respective expectation, okay, which I'm also going to prove today. Now, take a look at this guy now. What he's trying to tell us is that the expected value of X that we're looking for can either be 0 or greater than 0. So which means non-negativity is actually ruled out. Okay, non-negativity is actually ruled out. That is what we mean. Okay, so take a look at that. So this is one of the axioms of expectation. Now, when you take a look at this guy now, if I have expected value of AS, where A is a constant, okay, we can write it that way. For instance, take a look at this example, expected value of 5x. Okay, if I have expected value of 5x now, okay, give me 1 second. So I'm currently working on this guy now. Okay, expected value of 5x. Okay, because 5 is a constant, so 5 is going to come out, and I'm going to have expected value of X. Look at that. So it's going to be 5, the constant multiplied by the expectation. So that's a rule which I basically want you to see. Okay, that is a rule that we basically want to see. And you know what? For any random variable S and any constant A, and the expected value of Y equal to 1, so that is when Y is a constant random variable, where you're doing this mapping. And you know what? We can also have a constant function. For instance, expected value of 5 is basically 5, because the expectation of a constant is a constant. It's just like you put money in your pocket, you put $5 in your pocket now, provided that no external force acts on that, you're still going to save $5, okay, in 5 years. Okay, which means the expected value of a constant would basically remain a constant. Okay, so that's exactly what I'm trying to say here. Expected value of 1 is basically going to be 1. Okay, I just wanted to take note uh, of that. And the reason being that the expected value of a constant is always going to remain a constant. So, if you look at the axiom 1 to 4 now, if you look at that, we are actually talking about the axioms of expectation. This hold all the time. So these are rules, okay? These are rules, okay? If you're given set of data set now, of course, we can actually investigate this, and we can establish that. So take a look at number 1, which I call the expectation of the sum of random variables, and that is equal to the sum of the expectation of the respective variable. And of course, if you look at number 2, it's trying to tell you the expected value of S. This guy, for the condition under which this guy hold is when S is greater or equal to 0. Okay, you're gonna, the moment S is not, it's trying to say, before I can have my expectation to be non-negative, then the support of the random variable also has to be non-negative. So this is a conditional statement, so which I basically we wanted to see. I think a chat came in and somebody said it's assume two and if and only if, or yeah, that you are right. That's what I'm saying now. Because I want to also tell you there is possibility that we get an expectation can be negative. I just wanted to say we can have a situation where maybe a expected value is -6. Okay, so the only condition to have this guy now is the support. When the support is non-negative, the expectation of X that have that support should also be non-negative. That's exactly what we mean in axiom 2. Okay. And in Axiom 3, of course, I think I've demonstrated that. Okay. I've actually, somebody said, Axiom something that can be proven, or they are just rules we will use to build off to. Oh my God, that person has asked a very good question. Now they can be proved. I'm actually going to prove one for you now. You're going to see. But you know what? Before I go into proof, I first want to unfold them. I just want to show, I'll give you these rules. Now, if I want to prove, okay, basically, if I want to prove this guy now, okay, I'm going to show you how to prove that one and how to also prove this guy now. Okay, now let's get started. Um, I'm going to stop my share now. Okay, I'm going to stop my share now, and I'm actually going to use my whiteboard. Give me 1 second. I'm going to use, and I need you to confirm if you are actually seeing my whiteboard. Can you confirm if you're seeing my whiteboard? Can everyone confirm if you're seeing my why? Okay, thank you so much. Now, somebody shares with me right now. The person said, can these rules be proved? Oh my God, before they can become rules, it means they have already been established and they've been proved. And you know what? Oh, somebody said, actually, no. Okay. Does that know me? Oh, you cannot see. Okay, give me 1 second. I'm actually gonna reshare now. Somebody said they can't see what I'm sharing now. Give me 1 second. I think I'm gonna reshare it. What about now? I needed to confirm if everybody is seeing what I'm sharing now. Is everybody seeing that? Okay, I need
Yeah, I can see it now.
now you can see, okay, which means everybody can see now. Thank you so much. Okay, we actually, because this course is actually called the theory of statistics. And of course, what we do in theory of statistics is basically, to establish some statistical models that we are using in statistical analysis. This is a theory. Now, this is what I want to prove now. Expected value of X plus Y, okay, equal to expectation of X plus the expectation of Y. Okay, if I want to prove this, then since I have X and Y, okay, since I'm actually, investigating the joint, okay, X and Y, I have a bivariate right now, then I need a joint. F of X, Y. Okay, the joint F of X, Y. Okay, if I'm talking about the joint PMF, is basically the probability of this and the probability of that. Okay, I wanted to take note of that. So I actually did something like this yesterday when I was actually solving a problem that has to do with independence, the probability that S can take on any value, and the probability that Y can take on any value. The F of X, Y that I got now is actually, this is what we call joint PMF. Okay, we call that joint PMF. Now, if I want to find the expected value of X plus Y, okay, the expected value of X plus Y, recall when I'm talking about the expectation of X for discrete case, I'm actually going to have that F of X, you know that, right? If I want to talk about the one of X plus Y, I'm actually going to have to summation sign because I got two variables, and this is going to be X, this is going to be Y. And if I have that, because I have X plus Y here, I'm actually going to have X plus y, and you know what I'm going to get is going to be a joint that I'm going to use there. I wanted to take note now the expected value of x plus y, because I got two variables. I'm actually going to get to summation sign, and when I get to summation sign, I'm going to be using a joint PMF. Okay, I'm going to be using a joint PMF. And there's another thing I wanted to take note. Okay, if I have a joint PMF, let's say I want to get the marginal. Okay, if I want to get the marginal from the joint PMF, what am I going to do? I actually need to sum the joint PMF over the range of y, because I'm looking for f of s. The f of s is actually the marginal distribution of x. Okay, similarly, I also want you to take note, if I want to get the marginal distribution of y, okay, for a discrete case, I want to get, if I want to get f of y, oh my God, it's basically going to be summation. I'm going to sum this with the range of x. Okay, I'm marginalizing now. So this f of x, the f of y, the f of s, we actually call the marginal distribution, marginal distribution. I just wanted to take note of that. Okay, we have f of y, we have f of s. You can actually determine them from the f of xy. Now let's get back to business. Don't forget what we're doing in weight. We basically want to show that the expected value of, of x plus y, okay, equal to the sum of that. So what I'm gonna do now, okay, I'm right here now, right? I'm actually here, right? Okay, when this is guy now, okay, is basically, if I have x plus y, okay, I need to, expand that. I'm gonna use x to multiply by, so I'm actually gonna have this guy now, okay, plus, okay, then I'm going to use the whole thing now to multiply that. Okay, I'm actually going to have, okay, f of xy. Oh my God, take a look at that now. If you are not getting what I just did now, I need you to talk. I need you to ask me question. You know what I've done. I use summation, the x plus y to multiply the f of xy, and take a look at what I got. Take a look at that now. Okay, if you have that now, I can simplify this, as summation s, and that's a x, right? Then I'm going to say y, okay, f of xy, take a look at that, plus the summation y. The y is going to be in there. Then I'm going to have this guy now, then f of xy. Oh my God, if you don't understand what I just did now, I need you to ask question. Is there anyone who doesn't understand my step? Is there anyone needed to ask question? Oh, can you all confirm again if you can hear me clearly? Can
Yep,
everyone?
I can
Okay,
I can hear you
okay.
clearly, and I was also kind of confused on how you got to the last step from the step before that.
Oh, okay. So you mean you confused about? Are you talking about this guy, the second line? Are you talking about this one, the one I circle now?
Yes, I'm confused how you got there to the line after that.
Oh, to the line after that. Okay, what I just did is just like I take I actually take a summation. Let me see. Uh, take a look at this. You want to have S. S is going to go with that, which is this guy here. Okay, and the one that have Y, we go with the f of xy. That is what I did here. Do you see that now?
Yes, I do.
Yes. Okay, the same thing is what I did in the second one. Oh my God. Oh my God. Take a look at this now. So what does this one become? When I have this imaginary, right? Take a look at that. Take a look at this. The one I circle now. This imaginary. I just gave you imaginary the other time, right? If you take a look at that, you basically, if I want to rewrite, okay, take a look at what I have now. Expected value of x plus y, okay, is basically summation x. Okay, there's a x here, right? Then summation that f of xy, okay, plus summation y, summation x, f of xy. Look at this guy, and look at this guy. This is basically f of x, right? Let's imagine this is basically f of y. Do you remember that? That I said when you sum a joint with respect over the range of y, that is f of s. When you sum the joint over the range of s, that is f of y. Oh my God, what do I have now? You're going to see what that is going to lead to now. Oh my God, this is a party. And I need you to, if there's anyone who doesn't understand my party now, you need to ask question now. This is what I'm going to get. I'm going to get summation x. This is based on the whole of t in here is going to be f of s. And here I'm going to get summation y. The whole of t in here is going to be f of y. Oh my God, what is that? That is the expected value of s. Oh my God, what is that? That is the expected value of y. What have we just done now? We've just approved that. That is the proof. Take a look at that. That is the end of the proof. We have been able to prove now that the expectation of the sum of random variable x and y equal to the sum of the expectation of x and the expectation of y. That is the way to go about that. Is there any question on this before I move on? If you really understand what I've proved now, if you really understand this now, I need you to say yes or you comment yes. If you really, oh my God, look at me. Good job. Good job. Okay, thank you. Okay, now I'm going to stop my share now and I'm going to go into another section. Let's take a look at what we have right now. Okay, give me 1 second. So we are actually on linearity. Now we've been able to prove the first one. Of course, the second one is going to hold all the time. The second one is going to hold all the time. When the support of S is non-negative, the expected value of S also expected to be non-negative. But you know what I want to prove now? I want to prove the third axiom, which is expected value of AS equal to A expected value of S. Okay, if you basically want to prove that, let me stop my share now. Okay, now, excuse me. Now, I want to prove that the expected value of this is equal to this. Okay, how am I going to prove that? Okay, if I want to prove this now, it's like I want to say expected value of AX equal, so summation X, AX, I'm going to use f of X. Okay, and if I'm using f of S, this A is a constant, right? A is a constant, right? Okay, A is going to leave. A summation X, f of X, right? What is this guy now? So it's going to be A. That is expected value of X. Okay, now you just prove that now. Okay, you just prove that now. Okay, that is how that guy is actually is being proved. Now I think I'm going to show you more of I'm basically going to show you more of this. Okay, the more of this, I think give me 1 second. Let me see what of in a situation where I have I'm going to stop my share now and I'm going to share another thing. What if in a situation where I want to show this x plus a? What about a situation where we are adding a variable to constants? Okay, here, okay, a is a constant. A is a constant. And I want to find, I want to show that the expectation of this, expectation of this is basically going to be that when you add a constant to a variable, the expected value of, plus a. Rather. So if I had a constant to a variable, the expectation of the addition of a variable and a constant is basically going to give us that. So how am I going to do that? Then I'm going to have s plus a, then I'm going to have a summation x, then I'm going to have x plus a, then I'm basically going to have f of x. Okay, I wanted to take a look at that now so you can expand now. So x, okay, x, f of x, right? Plus, okay, summation s a f of s, right? When you expand that, okay, when you expand that, that's what you're going to have. Oh my God, this can be written as well. That is expectation of s, right? Plus, right here, I'm going to have a summation fs. Okay, summation fs, okay, the sum of a probability is actually 1. You know that, right? Okay, so this is going to be expectation of s plus a into 1. So automatically I'm going to have f of expectation of s plus a. So now that is already proved. Now that's already proved now. Okay, you know, some of you may be wondering, what is the essence of what we're doing now? What is the essence? Does it have any application at all? Does it have any application at all? Now I'm going to walk you through an application now. Okay, I'm going to walk you through an application now. Okay, I'm going to stop my share now. Then I'm going to have a new share. So let's have an example, okay, from a real life, you know, practical situation. Okay, now let's assume in roll it, roll it, uh in roll it betting, those of you that are familiar with the betting game, okay, in betting on a single number, okay, betting on a single number, pays, okay, 35 to 1, okay, okay, that is now, okay, give me one, so that is 4, okay, each $1, okay, you bet, with $1, right? For each $1 you bet, okay, for each $1 you bet, okay, you win, okay, you win $35, okay, for each $1 you bet. That, but there's a condition. The condition is that if the ball, okay, if the ball lands, okay, if the ball lands in that pocket, okay, if the ball land in that pocket, okay, if the ball land, okay, in that pocket, okay, now that is the condition. Now we're basically going to define what our X represent, right? Okay, if we let S represent your net winning, okay, if, okay, X denotes, if X, a random variable S, denotes your net winning, okay, if you denote your net winning, then we're going to have a PMF, okay, giving us this, we're going to have a kind of a table, okay, -1, 35, okay, 37 over 38, okay, and 1 over 38, okay, because the probability of you winning, that, so you were given this, okay, take a look at that, -1, 35, and of course the corresponding probability is actually that, which I want you to see, okay, right here now, you can find the expected value of X, right? We just say, what is the expected value of winning? Okay, what's our guess? Okay, the expected value of X is basically, you're going to be multiplying that, then you're going to add up. Okay, you
Professor,
basically, okay, go ahead.
should the probabilities be 1 over 36, or is it over 38?
It's here, we know you are given this probability.
Oh,
So
okay.
this one is given.
Okay, got it.
Yeah, so, okay, so now the next thing I want you to see now is, that is for X. Now, what if in a situation now, okay, where we want to define a new variable, W, okay, let's define, okay, a new variable, okay, a new variable W, okay. Now, that new variable W can take only 0 and 1 with the same probability. If we can take 0 and 1, then that is looking like a binomial, right? Okay, so W, okay, the probability of W, 0, 1, okay, the same probability, okay, and if that is the case, now the question now is, we want to, S can be defined in terms of W, where X is basically going to be 36 W minus 1, okay. Now if they define, if you have a variable, let's say X, okay, equal to 36 W minus 1, okay, let's say we have this guy now, okay, and we want to find the expected value of X. If you want to find the expected value of X, okay, now what we're going to do here is, given the table now, I'm going to show you something now. You got your table now, okay, which I wanted to see, okay. Now, if I have X equal to that and I want to find the expected value of X, okay, maybe I want to find the expected value of X without knowing that this exists, without knowing that the X and P of X exists. I want to find the expected value of X from the W, which means I'm actually going to make use of this. So which means it's going to be expectation of 36W minus 1. Expectation 36W minus 1 is basically going to be 36 expected value of W minus, okay, when you take a look at what I have now, so you're basically going to see that this is going to be like expectation of minus 1, okay? And in that case now, so we basically going to be 36 expected value of W, and expectation of minus 1 is minus 1, so which means I need to find the expected value of W. And expected value of W can be found using expected value of W can be summation W, the P of W. So which is going to be this times that times that, then you just add up. And when you add up, whatever you get, you multiply by 36, you subtract 1 from that. So this is one of the, example of that. And now you're basically going to see it's going to give you 36 into the expectation of W is going to be 1 over 38, then minus 1. Then you're going to get your result. And in this case, it's basically going to give you negative. Okay, you're going to have negative 2 over 38 when you find the expected value of W. So why do we have that? We have that because when you look at X, one of the support of S is negative, it's minus 1. Look at that. That was why the expectation will lead to negative. If you look at the axiom number 2, okay, now somebody say, how did you get 36W minus 1? The 36W minus 1, okay, is actually arrive at, if you look at the relationship between these two, okay, if I plug in 0, okay, here, I'm going to get this minus 1. Look at that. Plug in 0 into this. Okay, it's going to give you minus 1. If you plug 1 here, it's going to be 36 minus 1, that will be 35. So which means the relationship they got is defined by this. Okay, I look at the 2 PMF and I bring out this relationship. Okay, that is how I got that. Okay, you're welcome. Now I'm going to stop my share now and I'm going to go into the material. I think I'll spend more time on that. Okay, I'm going to go into the material now. Okay, and you got to know expectation of a constant is a constant. Okay, a constant doesn't change. So these are the rules. Okay, and you know what? I want to go into this. Expected value of xy is not the same as this. Take a look at this. The only condition under this can hold is when x and y are independent. When x and y are independent, then we can have expected value of xy equal to expected value of x multiplied by expected value of y. But we could have a situation where they are independent and they are not. If they are not independent, what I'm showing you now does not hold. Okay, what I'm showing you now does not hold. Okay, now expectation of the different, we've just talked about the expectation of the addition of x and y. We can also talk about the expectation of the difference between them. So it's basically going to be that. You can prove that how. Okay, it's going to be that. So I just wanted to take note of that. Okay, now I think I've already proved this to you. Expectation of a plus bs is basically going to be that. Okay, we've already established that. Okay, now we can generalize now whether plus or minus is basically going to be that. Okay, and you have to know the support of x is actually that one. The expectation of x is expected to be that. So these are the rules that I talk about. Okay, these are, now we can now generalize. Okay, we'll be talking about x plus y. What about a situation where we have so many variables and the expectation of of addition of variables is basically going to be equal to the addition, to the sum of the expected value of the respective variable. So that is being generalized now. Okay, that's a generalization. Okay, and you know what? We can also generalize that of a constant. Okay, when you have a constant and a variable, you are adding them up. Okay, you remember the other time when I said the expectation of A and X, where A is a constant, I said is the expected value of that, right? Okay, now when I'm adding them up now, okay, we're also going to have that. Okay, that has been established. I just wanted to take note of that. Okay, now we now want to apply the linearity now. Okay, we want to apply that to distribution now. You remember yesterday when x1, x2 up to xn, when each of that follow Bernoulli distribution, okay, when you follow Bernoulli distribution, okay, of course the sum of that is actually going to be binomial. But you know what? I basically want to do this now. Oh my God, if you take a look at this now, when x1 and x2 up to xn, okay, are random variable and they are having the same expectation. What am I trying to say? Expected value of x1 equal to mu, expected value of s2 also equal to mu, until I get to expected value of sn or equal to mu. Okay, then if I add them up, okay, if I add them up, it means the expected value of x1 plus x2 is basically, it is expected value of x1 plus expected value of s2. Since they have the same mu, it's going to be mu plus mu, and I'm actually going to have 2 mu. If there are 3 variables, it's going to be 3 mu. If there are 4 variables, it's going to be 4 mu. If there are n numbers of variables, then it's basically going to be n mu. That is what we mean. You know why? Because they have the same expectation. Okay, so that is exactly what we mean. Now going into the Bernoulli now situation now, of course, we established that yesterday that when X follow a Bernoulli distribution with a parameter P, when I had, where X1 follow Bernoulli, it has, if X1 follow Bernoulli distribution, okay, with a parameter P, and X2 also follow Bernoulli distribution with a parameter P until you get to Xn, follow Bernoulli distribution with a parameter P. Then if I now want to get a sum of a random variable X1, X2 until we get to, Xn now, okay, now what we're actually going to say, okay, if I want to use the idea of the linearity of expectation now, where I basically want to add all of that together, okay, take a look at that, okay, until I get to Xn, okay, which is also going to be the expected value of X1 plus expected value of X2 until I get to the expected value of Xn. And don't forget, each of them has a PPP, right? Okay, have the mean of PPP, okay, because the mean, when X follow Bernoulli distribution, the mean of X is P. When I add them up, depending on the numbers of them, automatically that will be NP. And the moment you have NP, automatically you are referring to binomial distribution. Okay, so take a look at that now. We are using the knowledge of the linearity of the linearity of expectation now to go from Bernoulli to binomial. The one we did yesterday, the one I walked you through yesterday, I was actually using the knowledge of independence yesterday to figure that out. But today, I'm using the knowledge of linearity of expectation. Okay, now that is that. Now, why axioms? Of course, we need axioms and rules. And if you want to get things right, we basically need to understand rules. Okay, so that is why we need axioms. Now, the next thing on the line today is what we call variance. And let me tell you this, if you don't want to talk, when you mean is an average, expectation of X an average, you know that, right? And how do we actually, the expectation of X is actually the best guess we can have before we observe. And if you really want to know how reliable is our, is our guess, of course, we basically need to find the variance. Okay, the variance is basically going to tell us now how far we X, okay, the X be from the mean when it is observed. Okay, but let me tell you, before you go into observation, now you have a best guess in your mind. Like if you want to go to gas station before, if you want to figure out what is the gas price before you even visit any gas station at all, you have a particular values in mind that could be the price. Okay, when you after you now go to the gas station to make an investigation about what the gas price is, then how far will that now be from the mean? Okay, when you observe that, that's exactly what we mean. And you know what, we got a formula for that. If I want to find the variance of S, the statistical theory, variance of S is very, very important, because the variance will actually enable us to to be able to tell how reliable is the mean. And let me tell you this, our variance that we talk about is an expectation of a function. Take a look at that. Okay, expectation of a function. Look at that, which is expectation of x minus mu all squared. Take a look at that. That's a variance. Mu this time around is your guess. Now, when you take a look at this now, it's like you are looking at the distance between what is observed and your best guess. I told you the other time, your mind can never be empty. Okay, somebody said, since we expect s to be equal to mu, we didn't. Okay, so let me just go through the chart. Since we expect s equal to mu, isn't expected value of x minus mu exactly equal to 0? Yeah, you are right. Okay, expectation of x minus mu equal to 0. You are right. You are very, very correct. Okay, now good job. Now, yeah, but I'm trying to square, we are squaring this. Okay, we are squaring that. When you square that, we don't expect it to be 0. But what you just said now, expected value of x minus mu, okay, it is 0. But when it is squared, it is not equal to 0. When it is squared, that is the variance. The variance must exist. Okay, because you can never have a situation where your guess would be exactly as what you observe. I told you the other time, we live in a world where we live in a probabilistic world, and the statistical model that we are actually using can never give us an exact reality. I'm going to say that again. It can never capture exact reality. Therefore, the variance can never be equal to 0. Okay, the variance must exist. That is exactly. But somebody is going to say, in theory, variance can be 0, but that is not realistic. Okay, that was why we're placing a bound now here, that okay, variance of S can be greater than equal to 0 or greater than 0. But I want to tell you now, in reality, we don't expect, the variance is not expected to be equal to 0. Okay, I just wanted to take note of that. Okay, now if I now now you can see the formula for finding the variance now. Okay, we can actually use this on on different kind of distribution. How can we use this to find the variance, okay, of a Bernoulli distribution or of a binomial distribution? Okay, now the parameter, mu is expected value of x. And for Bernoulli, it is P. You know that? And that was why we plug in P to represent mu. And we basically going to have this guy here. Okay, now you can be asked to prove how do we actually obtain the expectation of x minus p all squared, okay, to be equal to that. I'm basically going to show you now. If I have expected value of x minus p or squared, okay? Now, if you expand this now, okay, you're basically going to see that you're going to have s squared minus 2xp, right? Plus p squared, right? Look at that. That's what you're going to have, okay? And you know what? This is going to be expected value of s squared minus 2p expected value of x plus expected value of p squared, okay? Okay, and parameter is fixed, right? Okay, so here expected value of s squared minus 2p. What is the expected value of s in that? That's going to be p, right? Then plus, what is that? P squared, right? So this is going to be expected value of s squared minus 2p squared plus p squared, automatically, you're basically going to have that, right? You're going to have the expected value of x squared minus p squared. And let me tell you, in Bernoulli distribution, expected value of x raised to power k equal to p. What do I mean? Expected value of x is equal to p, expected value of x squared equal to p, expected value of x raised to power 3 equal to p. If I have that now, so here I'm going to plug in p minus p squared. Okay, when you factorize that now, oh my God, when you factorize that now, it's going to give you this guy, which is basically what it got. Look at that. Look at the way I expanded that. Look at that. Okay, I'm using the idea of linearity of observation now. Take a look at that. So those ones are already established. Okay, so that is for the variance. And I think I just told you why we need a variance the other time. But let me tell you this. It is not the variance that we actually need. We need a standard deviation. You know, some of you may be wondering, what is the difference between variance and standard deviation? The variance is measured in square units, but the standard deviation is measured in, it's not measured in square unit. If you look at your mean is not in square units, but variance is in square units. Okay, therefore, we need to have a measure that we have the same units as the mean. And that is the reason why we're going to find a square root of the standard deviation. Finding the square root of the standard deviation, you're basically going to have the same units as the mean. Okay, and that is the reason why in statistical analysis, attention is on the standard deviation. Okay, so that is what I mean. Okay, when I say a square unit, this is what I mean. Square unit. Variance is in square units, because when you are finding the variance, you square. But when you are finding the mean, you don't square. Therefore, we don't use, if we want to tell how reliable is our mean, we don't want to use variance, because variance and mean, they are not in the same unit. Okay, and that is the reason why we need a square root of a standard deviation. I mean, the square root of a variance, because the square root of a squared, we return it back into the unit of the mean before you can actually tell how reliable is the mean. You're actually going to use a measure that have the same unit as the mean. So what I'm trying to tell you now, the standard deviation has the same unit as the mean. That's what I mean. Okay, so that is all about that, why we use standard deviation. And of course, what I did the other time, this is how you can expand that. Look at that. Okay, that is how you can expand that. The variance of x can also be written that way. So where we can actually say expected value of x squared minus expected value of x or squared, because mu is the same thing as the expected value of x. Okay, I just wanted to take note of that. Okay, so far so good. So I think I've already proved all of that. Now, there's something I'm going to show before I go today, and it's going to be, I'm going to say today I'm going to spend, those of you that have lecture at 9:50, 9:55, you can log out, because I'm still going to spend more time. Because I'm recording this. Okay, this is going to go into recording because I basically want to show. So today I'm going to show why, if I want to find the variance for in binomial distribution, okay, what and what do I need to do? Okay, if I want to find the variance, I'm going to show that. Okay, all that. Okay, then I'm also going to talk about discrete uniform distribution, getting the expectation as well. Okay, I'm going to show all this. Now, I'm going to stop my share now. Like I said, I'm spending 5 more minutes. Okay, but for those of you who have lecture at 9:55, you can actually log out. This is being recorded. Okay, now this is what I want to do. Okay, when you have a binomial distribution, okay, X follow binomial distribution with N and P. Okay, I want to show, okay, I think I showed you yesterday, expected value of X is actually NP. Okay, but what I want to show today, the variance of X is NP into 1 minus p. And that's exactly what I want to show now. So how am I going to show this? Now, if I want to talk about the variance of x, okay, I said it is expected value of mu all squared, right? Don't forget I said it's expected value of mu all squared. And you know what? The expected value of mu all squared, we have also have it to be this. Okay, we have also proved that it is equal to that. Okay, now expected value of this guy now minus, for binomial, okay, the expected value of x is np. I'm basically going to have np squared. So here I have expected value of s squared minus n squared p squared. But what I need to figure out now is the expected value of s squared. Okay, I need to figure out the expected value of s squared. If I want to figure out the expected value of s squared, I actually need a PMF of the binomial distribution. You can take the picture now, or you can take a screenshot, because I'm actually going to clean up. Okay, now what I'm going to do now, I'm going to go into binomial distribution now. Okay, binomial distribution, the f of s, okay, the probability of x equal to a realized value is n that, then p raised to power x, 1 minus p raised to power n minus x, and of course s start from 0, 1, 2 until you get to n. Okay, now I want to find the expected value of s squared. Okay, and what am I going to do to find the expected value of s squared? I need to go mathematical. Okay, somebody said, why is expected value of s equal to np? Shouldn't it be p? For binomial, expected value of s is np, but for binary it is p. Okay, I want the person to take note, the person that just chat with me. For binary, the expected value of s is p, but for binomial, expected value of s is np. Okay, I believe the person has taken note of that. Okay, the person that asked me the question right now. Okay, now if I want to get the expected, this guy, I already have this guy, but I need the expectation of s squared. But you know what? I should be able to write that. What is s squared? Okay, I can write s squared as x. I'm going to use the idea of factorial. You remember yesterday when I said 5 factorial, I'm actually going to be going down. Do you know that this guy is the same thing as that? Let's see. Is s squared the same thing as x into x minus 1 plus x? Yes, because when I expand that, it's going to be x squared minus x plus x, which is the same thing as x squared. Okay, now if I basically now want to find the expected value of s squared now, okay, if I want to find the expected value of s squared now, then it means I need to find expected value of x into x minus 1, then plus expected value of x. Okay, and you know what? It means what I just need now is expected value of x into x minus 1. I already know this guy to be np. Okay, if I want to rewrite the old scenario now, if I want to have write the old variance of x now, okay, I'm actually going to write expected value into x minus 1, okay, plus np minus n squared p squared. That is what I'm going to write now. Okay, the moment I have this guy, the only thing that I need to figure out now is this guy. I need to figure out the expected value of x into x minus 1. That is exactly what I need to figure out now. Okay, if I want to figure out now, that I'm going to do expectation into x minus 1 is going to be equal to summation s into x minus 1 f of x. Okay, whereas s start from I'm going to use where s start from something to something. So this is I'm actually going to have x here, and so now when you take a look at this now, the f of s is actually the binomial distribution, so which I'm actually going to plug in. Okay, which I'm going to plug in. So what I'm going to do now, okay, I'm actually going to plug that in now. Okay, if you are following the proof, I'm actually going to plug that in now. Okay, plug it down here now. So the expected value now, the expected value into x minus 1 is basically going to be summation x into x minus 1 and combination x p raised to power s 1 minus p raised to power n minus x. Okay, I just wanted to take note, okay, of that now. Okay, so that is basically what I'm going to have. Okay, now when I have this guy now, so when I have this guy now, I think I'm still going to keep this one here so that you know where we are going. Expectation of that. Okay, now, when I have this guy now, okay, I'm actually going to have summation x minus 1. Okay, this is going to be n factorial divided by n minus x factorial p raised to power x, 1 minus p raised to power n minus x. Okay, and you know what? Since I have, x into x minus 1, okay, so I can rewrite this guy now. Give me 1 second. Uh, so x into x minus 1 is what I have now. Okay, so now I'm going to have summation x into x minus 1. N factorial is going to be n into n minus 1, n minus 2 factorial. So p raised to power x, 1 minus p raised to power n minus x. And I'm going to have n minus x factorial. And the x factorial can be written as x into s minus 1, s minus 2 factorial. So this guy, we cancel that guy. Okay, take a look at that. And when that guy actually cancel out now, okay, what am I going to have? So right here, and I can introduce p squared and p raised to power minus 2. When I do that, so I'm going to have n into n minus 1 p squared. Okay, then I'm going to have summation, okay, into n minus 2 factorial. Then I'm going to have x minus 2. Okay, then I'm going to have 1 minus p raised to power n minus x. Okay, then divided by n minus x factorial s minus 2 factorial. When you take a look at this guy, okay, it's basically going to be 1. Okay, because if you look at that, it's basically going to be 1. Okay, and when that guy equal to 1 now, okay, so when that guy equal to 1 now, okay, you're actually going to have n into n minus 1, then you have p squared, right? So take a look at that. So this is going to be 1, and if that is 1, so what I'm going to have now, so you're going to see what I'm going to write now. So uh so the expectation into x minus 1 is n into n minus 1 p squared. Okay, now if you have that one now, the next thing that we're basically gonna do, we're gonna go into the variance formula. Okay, we're gonna go into the variance formula. Okay, now the variance formula actually said the variance of x. Okay, we have expectation into x minus 1, okay, plus, okay, np minus n squared p squared. So we're going to plug in this guy now. So we have n into n minus 1 p squared plus np minus n squared p squared. Okay, when you expand that, I'm actually going to have n squared minus n, right? P squared plus np minus n squared p squared. And of course, when you multiply that, n squared p squared minus np squared plus np minus n squared p squared. This guy cancel that guy. Okay, so what do I have now? np minus np squared. Okay, when you factorize np into 1 minus p. Now take a look at that. So that is how to prove the variance of a binomial distribution, okay, to be np into 1 minus p. Now, what I'm going to do now, I will quickly walk you through that of the discrete transform, the discrete uniform before I go. Now, the discrete uniform, I think I've already explained that when you have a random variable x, it will follow discrete. If it is discrete uniform, they are equally likely. And you know what? In discrete uniform, okay, f of x in discrete uniform is 1 over n. I think you know that, right? Now, if I want to find the expectation of x, okay, I'm going to use summation x f of x, right? So which is going to be summation x. The f of x is 1 over n, right? Now I'm using my X equal to high here. Okay, that was why you see it's basically going to be 1 over n summation S. That is why you see that. Okay, now an X is a discrete. We're talking about natural number 1 to n. Okay, now if you take a look at this now, expected value of X 1 over n, so it means 1 plus 2 plus 3 until you get to n, right? Take a look at that. Okay, and when you take a look at this guy now, that is a sum, sum of n time. That's arithmetic progression, right? Okay, sum to n time in arithmetic progression, okay, is actually n over 2 into the first time plus the last time. You remember that? The sum to AP. So which is going to be, so I'm talking about the one here, okay? So n over 2 into, what is the first time? A equal to 1. What is the last time? N, right? So you have that. Okay, you have n plus 1. Okay, so this guy here, the sum of that is basically going to give you this. Now, what is now the mean? Expected value of X. Now, 1 over n, okay? N over 2, okay, into n plus 1. N cancel n. What do you have? N plus 1 over 2, okay? N plus 1 over 2, okay? And that was how you actually got this. That was how you got that. Okay, the expected value of X is n plus 1 over 2 for discrete. Okay, and you know what? If you want to do the variance for that discrete, okay, of course, the variance, you'll be expecting to have, what is the expected value? The variance of X is expected value of X squared minus expected value of X all squared, right? So which means here, the variance of X equal to I, you need the expected value of I squared minus, okay, the expected value of X. We've already found that to be n plus 1 over 2. You just square that. But I squared, okay, according to the law of natural, when you're talking about an arithmetic progression, this is a formula, summation of I squared equal to that. Okay, summation of I squared equal to that. Or what you just need to do now is just to make a subtraction. Okay, so here, if you take a look at this guy now, okay, this is a natural one for it. And don't forget, we've gotten this before, right? You just need to simplify this, and automatically you're going to get this result. Okay, you're going to get the result here. Okay, so that is the end of this material. So you can just look at that and see. So this is where I'm going to stop today. Very sorry to spend more time, but like I said, this is being recorded. Okay, until tomorrow that I'm going to come your way again. Make sure you stay safe and have a very beautiful day. I'm also going to start my office hour immediately I log out. Okay, you can log in if you want to come into my office hour. So bye for now, everyone.